Alright, so I'm just going to walk through a demonstration of the application. Um, so the idea behind the application, first of all, is to evolve a set of neural networks using a genetic algorithm to control the steering of organisms and direct them toward prey and away from predators. Currently, the only working example I'm going to show in this video is directing them towards prey. So why don't I go ahead and show an example to start off so you can get an idea of what I'm talking about. So I'm just going to run the very vanilla basic simulation here. What we see some green life forms, which are codenamed gnats, and they're hunting down the blue food, which I just call mushrooms. And their steering right now is controlled by a neural network, and the neural network takes as input a vector to the nearest prey, and also as another auxiliary input, the current direction that they're looking. And you can see the direction they're looking if I pause it for a second by the little black line kind of drawn. That's where they're looking currently. And the output from their neural network is the way they want to turn themselves. So a positive 1, which is kind of the max value, simulates or says they want to turn a hard right, whereas a negative 1 says they want to turn a hard left. And this is the output from the neural network. So we can actually look over here. I have this gnat here selected, gnat 34. And if we look at the bottom right, there's a display panel showing us some basic information. He's eaten 4 mushrooms during this generation. You can see the direction he's looking. This is just in radians. So we can also look at the inputs. These are graded between 0 and 1, so these are a little tougher to understand intuitively. But the first 2 inputs are polar coordinates to the nearest prey. So for this gnat in particular, the nearest prey is going to be this food number 23. And so the first one is, it's graded between 0 and 1, so it's hard to understand what this number means, but this is the direction of food 23 with relation to the gnat 34. And the second one is the distance, once again graded from 0 to 1. They have a max object view range, so they can only see something so many pixels away, and which would be a 1. Anything greater than that is just clamped at 1. They can see infinitely. I should reword that. They can see as far as they need to, but anything farther than a certain number of max pixels away is just kind of a max value for very far away. The next 2 numbers represent the polar coordinates for the nearest predator, and there are no predators to the gnat species here, so they're just zeros. And finally, this is it's looking graded between 0 and 1. And we know this is a very low value here. The lowest it could be is negative pi, because it's representing in radians, so it goes a range from negative pi to pi. And so the input here is very low. This is graded between 0 and 1 again. So the neural network, each frame will calculate the output and the desired turn of this gnat. We can advance frame by frame and kind of watch him move. And he's currently turning right slowly. Now at the beginning of this simulation, all of the gnats and all of the organisms, all of the brains, have just random numbers controlling how they're steering. And the simulation uses a genetic algorithm to evolve these neural networks toward an optimal solution. The fitness is calculated by the number of things that each organism eats per generation. And if we look down here, we can see we're currently on the 3rd generation, and generations take 2,000 frames by default. And this is kind of the sample size when we gather empirical data about how good each gnat is at finding food. And after 2,000 generations, which is coming up real soon here, we will see the generation increases after 2,000 frames. And all of these gnats now have a new unique ID number, which is higher than the previous ID numbers, because they each have new brains, evolved from the previous generation. We have a couple controls over here. I'm not going to get too into it. We can pause. We can advance frame by frame. We can restart the simulation with the same parameters. So if I click that, here we have, right back at frame 0, all new random brains. And we can also export the brains to a file. I'm not going to get into that. We can reset up the simulation, which I'm going to do in a few seconds. We can also opt not to show the labels for a simpler view. When we don't have an organism selected, when we have one selected, actually, you'll see some description of the life form down here. When we don't have anything selected, you'll see some genetic statistics. So you'll see this is the 0th generation. Well, the result of the 0th generation was the total fitness and the maximum fitness and the average fitness for each organism. Well, each species. And here are gnats, the only ones that are in the simulation, so this is the only really area we're looking at. And a generation just passed there while I was talking, so now the results of generation 1 are in, and here are the new values. Now once you have a few generations in there, so we're going to wait till the generation ends, which it will in just a second. There we go. We can click graph, and this will just show us a graph. I'm just going to shrink this down a little bit. This will just show us a graph of generations along the x-axis and the fitness values along the y-axis. And the lighter line here, at least as generations pass, this graph gets updated. The lighter line is the average fitness, and the darker line is the maximum fitness. And so here we can see the gnats aren't really learning, but this is to be expected with such a small number of generations. You need hundreds and hundreds of generations for the gnats to actually start to improve at their task. Right now they're not even doing that much oscillation, really. They're pretty static here. So that's just, you can view a graph there. So now I'm going to go reset up the simulation, and we're going to look at a couple of these options that I can set.